Graph traversal algorithms aim to visit all nodes of an underlying graph, and are probably some of the most important algorithms in graph theory. The two most popular algorithms in this context are BFS and DFS, which are useful for many applications. They can be used, for instance, for the people you may know feature of social networks like Facebook, or for the generation of mazes. Throughout this video we will deal with many applications of these algorithms and the key ideas behind their implementations. So welcome to Chapter 3, Graph Traversal Algorithms. Before we start dealing with graph traversal algorithms, we have to specify the definition of a tree. A tree is simply a connected graph that contains one fewer edge than nodes. Equivalently, one can also replace connected with acyclic in this definition. Trees are minimally connected, meaning that the removal of any edge would make the graph fall apart into two disconnected components. A tree is also maximally acyclic, meaning that the tree itself is acyclic, but the addition of any new edge would immediately create a cycle. Now, why do we even need the definition of a tree? Well, graph traversal algorithms try to visit all nodes of a graph and create a discovery tree during their execution, which is always a tree, or at least a collection of trees. Now that we are aware of some equivalent definitions of a tree, we can consider a detailed overview in which the focus lies on the application range of BFS and DFS. The BFS algorithm starts with an arbitrary node which receives a level of 0. The level of a node represents always the distance from the starting node to the specific node. In this video, the starting node will always be colored in blue. Once the starting node has been visited, the algorithm will visit all its neighbor nodes, which receive all a level of 1. The key idea of the algorithm is to always visit the neighbors of the nodes first that have also been visited first. Therefore, we proceed here by visiting the neighbors of the yellow node. Then we visit the neighbor nodes of the node that has been visited after the current processed node, and so on. Of course, the whole level assignment process can also be applied to the DFS algorithm, which traverses somehow through the graph until all nodes have been visited or until it gets stuck. If it gets stuck, it backtracks along the discovery tree to the last node that has unvisited nodes in its neighborhood and proceeds similarly. The BFS and DFS trees are often visualized with arrows to easily backtrack from a node to the starting node. But of course one can transform the arrows also into lines. In this case it becomes then immediately visible that these graphs are minimally connected. From the current picture it becomes clear why the one graph traversal algorithm is called breadth first search and the other one depth first search. A nice application of the BFS algorithm is the knight's shortest path problem, which involves finding the shortest path for the knight on a chessboard from a specific starting square to all other squares. This problem can be solved by simply applying BFS on the knight's graph of the corresponding chessboard. To obtain now the shortest path from the blue starting square to an arbitrary square, we only have to follow the arrows in the BFS tree in the opposite direction. For an application of DFS, let us consider the creation of a maze, which is basically an application of DFS on the following graph. Note that the maze here is really nothing else than a small aesthetic modification of a DFS tree of this graph. To obtain a solution from our starting node to the node in the bottom right corner, we have to follow the arrows in the opposite direction starting from the target node. Analogously, one can find obviously paths to other target nodes. In graph theory, one uses DFS or BFS very often to check whether a graph is connected. Remember that both algorithms aim to visit all nodes of a graph, starting from one specific node. And if the execution of BFS or DFS on a graph has been terminated, and not all nodes have been visited, then it's clear that the graph is not connected. Furthermore, one can start the algorithm then again from a node that has not been visited, to determine the connected components of the graph. A very important use case of DFS and BFS is the cycle detection, that we will consider here using DFS. Do you see how we can conclude during the execution of DFS that the graph contains a cycle if one exists? The idea is actually very simple. If DFS encounters during its traversal a node in the neighborhood of the current processed node that has already been visited, then it can terminate immediately with the message that the graph contains a cycle. Another important application of DFS involves finding a topological sort of a directed acyclic graph. In this graph, every node represents a task, and a directed edge like this one here that points from task 1 to task 2 means that task 1 must be done before task 2. More practically, you can imagine the tasks as being lectures at a university, and you must attend lecture 1 in order to attend lecture 2. We can obtain now a topological sort of this graph that is a valid order to execute all given tasks in this graph by applying DFS. The procedure works as follows. First, we simply apply DFS and wait until it gets stuck at a node. And whenever we reach a node in whose neighborhood all nodes are already visited, we put the node, or here the corresponding task, on a stack. Once this modified DFS algorithm has terminated, we can easily construct a schedule for the tasks with the resulting stack. And the order here is now as follows. First we do task 1, then task 2, then task 6, 4, 7, 3 and 5. For another application of graph traversal algorithms, remember that BFS and DFS construct a discovery tree during their execution. Such a discovery tree of a connected graph will always contain all nodes of the graph and is then a so-called spanning tree, which can be computed with different algorithms as well. In the following we will consider the exact definition of a spanning tree and probably one of the simplest algorithms to construct one. Let G be a connected graph and T a subgraph of G. Then T is a spanning tree of G if it is a tree, so it is acyclic with one fewer edge than nodes, and if it contains all nodes of the graph G. The most common algorithm to create a spanning tree proceeds as follows. First it adds all nodes of the graph to the current subgraph, which will represent the spanning tree at the end. Then it inserts step-by-step edges that do not create a cycle into the subgraph. The cycle detection here can be executed with DFS or BFS, as shown previously. The algorithm terminates then if the current subgraph contains one fewer edge than nodes. Such spanning trees have many nice applications, for instance in maze generation. Another application of graph traversal algorithms is Fleury's algorithm, an algorithm for creating Euler trails and circuits in graphs. In Chapter 1 we saw that Euler trails and circuits have been motivated by the Königsberg bridge problem, which was solved by Leonhard Euler in the 18th century. The problem involved deciding whether there's a walk through the Prussian town of Königsberg that visits every bridge exactly once. Regarding this, we considered a simplified model with 4 islands and 7 bridges representing Königsberg. And then the Königsberg bridge problem broke down into a graph theory problem, more accurately into the problem of finding a sequence of nodes in the graph, called walk, that visits every edge exactly once. In this context we considered some of the most fundamental definitions of walks in graph theory. Here it is important to point out that a tour through Königsberg that visits every bridge exactly once is equivalent to an Euler trail in the Königsberg graph if the starting and ending nodes are distinct, or to an Euler circuit otherwise. Very important here is Euler's theorem, which states that a graph contains an Euler circuit if all its nodes have an even degree, and that it contains an Euler trail if exactly 2 nodes have an odd degree. Furthermore, it states that a graph with any number of nodes with an odd degree other than 0 or 2 will not have any Euler trail. Using this theorem, we concluded that the Königsberg graph contains neither an Euler circuit nor an Euler trail, which is why the question of how to actually calculate such a walk never really came up. But the things here changed during the Second World War. Two bridges of Königsberg were destroyed, leading to a change of the degrees in the Königsberg graph, and implying the existence of at least an Euler trail, which can be computed using, for instance, Fleury's algorithm. But how exactly does this algorithm work? And what do graph traversal algorithms have to do with it? Necessary for the understanding of Fleury's algorithm is the definition of a bridge in a graph. And a bridge or a cut edge is an edge of a graph whose deletion increases the graph's number of connected components. The edge connecting the nodes 1 and 3 is, for instance, a bridge, since deleting this edge would cause the graph to fall apart into 2 disconnected components. More specifically, the graph was made up of 1 connected component before the deletion, and 2 separate connected components after the deletion of the edge. Note that also the edge connecting the nodes 3 and 4 is a bridge in this graph. Now, how exactly can we decide whether a given edge is a bridge of a graph? Or how can we even determine all bridges of a graph? To decide whether a specific edge is a bridge, one has to determine first the number of connected components of the graph, with a graph traversal algorithm of choice. Then one can remove the considered edge from the graph and determine the number of connected components again. If the number of connected components has increased, then the deleted edge was a bridge. Note that this procedure can be repeated with each edge to determine all bridges of a graph. But nevertheless, be aware that this is not the most efficient way to find all bridges in a graph. Since we know now how to determine the bridges of a graph, we can already consider the algorithm of Fleury. We will apply the algorithm on the following graph, in which exactly two nodes, the nodes 3 and 4, have an odd degree. Because of this, we can conclude from Euler's theorem that this graph must contain an Euler trail. Fleury's algorithm requires a starting node, which has to be a node with an odd degree if the graph contains an Euler trail, or any arbitrary node if all nodes have an even degree. In the first case, the algorithm would compute an Euler trail, while it would compute an Euler circuit otherwise. For the following, you can imagine that you are a person going for a walk through a town like Königsberg, aiming to traverse every edge exactly once during your walk. Starting from node 3, it's clear that we have a variety of different edges to choose from to move to another node. And one of those edges is also a bridge. And Fleury's algorithm tells us now that we are not allowed to take a bridge in order to move to another node, unless a bridge is the only edge that can be used. Now, what exactly is the logic behind this algorithm? The selection of a bridge at any step in the algorithm would immediately trap us in one connected component of the graph, since we are not allowed to use the same edge again. Furthermore, we can also temporarily delete the used edge from the graph. This makes it then clearly visible that we are trapped in a subgraph that is not connected to the rest of the graph, in which we have untaken edges left. So at the beginning we can use any edge to a neighboring node instead of the bridge edge. Again, the taken edge can be temporarily removed from the graph, and we can consider the adjacent nodes of the current node. In this case, there is only one edge to select, which is also a bridge. Note that this is the only case in which we are allowed to select a bridge, as there is no other choice to leave this node. The algorithm will proceed now in exactly this manner. So now we've seen many applications of graph traversal algorithms, and I'm very sure that you would agree that they seem quite important. But how exactly can we implement them? As mentioned at the beginning, the BFS algorithm starts with an arbitrary node, then visits all of its neighbors in a specific order and proceeds in the same way with the neighbor that has been visited first, which leads to the typical layer-by-layer exploration of BFS. In the following we will need labeled nodes, which is why we will shift the level of each node into a small rectangle within the node, and place its index below that rectangle. When we consider now the BFS tree in the animation, we see that the visited nodes of the graph are obviously colored in blue or green, but on a PC this has to be managed differently. A typical way here is for instance to create an array or a list that contains as many elements as the graph has nodes, where the entry at position I is 1 if node I has been visited and 0 otherwise. Similarly, levels and parents of nodes can also be stored in lists. The level assigned to node 0 is for instance 0, and its parent node is -1, which means that there is no parent node for this node. The next node, node 1, has a level of 1. And to find its parent node, we simply have to follow the arrow pointing to it backwards, where we see then that its parent node is the node 0. Analogously, we can insert the levels and the parents of the remaining nodes. But nevertheless, it is important to note here that these lists will be constructed while the algorithm is being executed. For a simple implementation of the BFS algorithm, we will need a very popular data structure called queue. For this, think about a traffic light and cars waiting in front of it. Now imagine that each car stores a number. In this case, the waiting cars can be considered as the queue. If a car passes the traffic light, which must always be the car that reached the traffic light first, then the queue becomes smaller afterward. The operation of removing the first element from the front of a queue is called the dequeue operation. In Python, a queue will typically be represented by a list, and if we denote the queue here with capital Q, then the dequeue operation can be executed by the command Q.pop of 0. The addition of a new element, for instance the element 9 to the back of the queue, is achieved through the enqueue operation, which can be executed by the command Q.append of 9 in Python. A queue ensures that the elements in the queue are processed in the order they were added, following the first in, first out FIFO principle. The BFS algorithm requires a description of the underlying graph, and an arbitrary starting node. In this implementation, the graph will be represented through an adjacency list. If you don't know what this is, please take a look into chapter 1. The first step within the function is then to determine the number of nodes of the graph, so that the parent, level and visit lists can be initialized with the proper dimensions. We will apply the algorithm here with starting node 12, which receives a level of 0 at the beginning as it will be the root node of the BFS tree. Then the starting node will be marked as visited and added to the queue. While the queue is not empty, we will execute now the following lines of code. We dequeue from queue, so we pop the first element from the queue and assign this node to U. Then we iterate over all adjacent nodes of U that are unvisited. For this purpose, one can either include an if statement into the upcoming for loop, or one can already create a list containing all unvisited adjacent nodes of U. For each node in this list, we execute then the following lines of code. We set the parent of the node V to U. We set the level of the neighbor node V to the level of the node U plus 1 and mark the node V as visited. And finally, we append the node V to the queue. And once the queue is empty, we can return the parent, level and visit lists. Before we execute now the next iteration of the while loop, we have to check whether the queue is empty. This is obviously not the case, so we execute the code inside of the while loop again. Note that the neighbor node of node 12 that has been visited first is the node in front of the traffic light in the queue, so the first element inside of the queue. In the following, we dequeue this node from the queue and determine all unvisited adjacent nodes of this node. Each unvisited adjacent node of the node 6 will get the node 6 as its parent, a level that is equal to the level of node 6 plus 1 will be marked as visited and appended to the queue. The algorithm will proceed in exactly this manner. Note now that all remaining nodes in the queue don't have unvisited nodes in their neighborhoods, which implies that nothing will happen in the following steps. So we've seen that BFS is basically a very easy algorithm to implement. And soon we will see that the same holds also for the iterative implementation of DFS. We saw already that the DFS algorithm, or more specifically the random DFS algorithm, traverses somehow through the graph until it has visited all nodes of the graph or until it gets stuck. In the second case, it would backtrack to the last node with unvisited nodes in its neighborhood and would proceed with the same strategy. But even though the mentioned approach is a very good way to remember the idea of the algorithm, there's actually a bit more happening when applying the typical iterative implementation of DFS. At the beginning of the algorithm, the starting node will be marked as visited and receives a level of 0. Then all nodes in the neighborhood of the starting node will receive this node as their parent and a level that is equal to the level of the starting node plus 1. The last node that was updated will then be considered in the next step of the algorithm and marked as visited. Similar to before, we update the parents and levels of all unvisited neighboring nodes of this node and move them to the neighboring nodes that has been updated last. So at the moment we obviously don't care about other nodes in the neighborhood of the starting node. We explore the graph in depth first. But what exactly happens if we get stuck? Basically, we push the nodes that have been updated onto a stack in each iteration, and then proceed in the next iteration with the node that is on the top of the stack. The backtracking here is now realized through the stack, but you will see in a moment how exactly. Furthermore, the main difference between the DFS and the BFS algorithm lies in the use of different data structures. A stack for DFS and a queue for BFS. Now what exactly is a stack? A stack is a data structure that follows the principle that elements are added to the top of the stack and also removed from the top of the stack. In general, the addition of a new element to the top of the stack is executed by the so-called push operation. In Python, a stack is basically nothing else than a list, just like a queue. And if we want to add an element to the stack, we simply append it to the list, just like for the queue before. The only difference to the queue concerns now the removal of elements from the stack. Here we don't remove the first element with s.pop of 0, but always the last element with s.pop. A stack works according to the last in first out LIFO principle, which is similar to stacking coins. In the following, we will apply the DFS algorithm using a stack on the following graph, and derive the code for this algorithm step by step. Since we will consider random DFS here, we have to import the random module to execute the upcoming code. The input arguments for DFS are obviously the same as for BFS, and furthermore the first 4 lines of code are exactly the same as well. After the initializations of the lists with the proper dimensions, we assign a level of 0 to the starting node and initialize a stack S that contains only the starting node. Same as for BFS, we execute certain lines of code while the stack is not empty. First, we pop the top element from the stack and assign this node to U. Once this has been done, the node will be marked as visited. This is also something you can remember. In DFS, we mark a node as visited once it has been popped from the stack. In BFS, on the other hand, the node will be marked as visited once it has received a parent and a level. After that, we consider all nodes in the neighborhood of the node U that are unvisited. The randomness comes now into play by the random shuffling of the list of unvisited neighboring nodes of U. For each unvisited adjacent node of U, we set the parent relation, the level, and append it to the stack S. Now we can let the algorithm run like this until something interesting is about to happen. Something interesting happens already in the next iteration of the while loop. The last node that was processed is the node 24, therefore it is also on the top of the stack. In the following, we pop this node from the stack, mark it as visited and process its unvisited neighbor nodes. Here we see that node 19 has node 23 as its parent, and therefore a level of 1. As we've seen previously, we will change now the parent of this node as well as its level. So node 19 gets node 24 as its parent and therefore a level that is equal to the level of node 24 plus 1. Now what is special or problematic about this situation? The problem is that if we push node 19 onto the stack, it will be there twice, because node 19 is also a neighbor node of the starting node, and has therefore already been pushed onto the stack previously. Now why is this a problem? During the execution of the algorithm, every node in the stack will be popped from the stack, marked as visited and processed. Why is that? Because the algorithm proceeds until the stack is empty, and the stack can only be empty if all nodes have been popped from the stack. And if a node occurs multiple times in the stack, then it's clear that at some point the visited node will be popped from the stack. Therefore, you will probably see in most implementations that there is also an if condition here that always checks whether a popped node has already been visited. But note that this is not the only way to avoid this problem. We can also use a function, here called removeDuplicates, that checks in every iteration whether the node V occurs twice in the stack after it has been pushed onto the stack. If this is the case, it will remove the node V from the stack that was pushed onto the stack first, leaving only the most recently added nodes. In this way, a visited node will not be processed again. Note also that the stack does not become too large for the visualization when using this approach. The whole process will be repeated until the stack is empty, and when the stack is empty, we will return the parent, level and visit lists. The video is now basically finished, but for the sake of completeness I will let the animation play until the end.